Hello, everybody, and welcome to yet another recorded Zoom interview. This time we go to New Hampshire, the New England portion of North America, University of Massachusetts Lowell, geology professor Rich Gaschnig. Rich, what's the weather report today in that little town in New Hampshire where you live?
Oh, it's beautiful. It started out in the 60s and it's supposed to get up to 80 today.
Ah, New England. And fall, is you got some color in the trees already?
Just a tiny bit, but it is dropping at night. Like we're getting down into like probably the 40s. So we are at that time of year, but we are in the middle of a drought, which is not great.
Okay. Well, we can talk about that for the next half an hour, Rich. I don't know, but no, I guess we won't. Viewers, Rich is back. He's been part of these interviews. I think this is maybe Rich's third appearance over the last few years. And today we talk about a brand new paper, a 2025 paper by Rich Gaschnig talking about paleogeography back in the Precambrian days, more than 1 billion years ago, with the Belt Supergroup. So I'm at it again. I'm talking to someone else about the Belt Supergroup, the fantastic and weirdly undeformed, flat-lying Precambrian rocks, best exposed, at least in my mind, in Glacier National Park in Montana, but we can go other places with Rich as well. So this is a 30-minute chat with Rich. We'll see where we go. Rich, what motivated this new paper? I know you've been working with the Idaho batholith, for instance, for a long time, and the Belt Supergroup is just kind of nearby, and you naturally went in that direction.
Well, I- actually, when I was like finishing my undergrad, I was like very interested in supercontinent reconstructions and stuff like that.
Okay.
But I just didn't really have an opportunity to work on it in grad school. And the other thing that I got really interested in when I started my master's was like detrital mineral stuff. Like the idea that like you could, go to the beach and like look at sand grains and try to figure out where they came from, I thought was just really kind of amazing. But again, I wasn't working, or I didn't really have the opportunity to do much of that until I became like a professor.
Nice. Well, we're definitely going there, and we've got some slides that we're going to look at, but let's just do a little bit more verbally here, Rich. Which supercontinent are we talking about? This is not Pangaea. It's older than Pangaea. And which continents are potentially in our discussion today?
Yeah, so this is the supercontinent that some people call it Nuna and some people call it Columbia. I generally prefer Nuna, but people debate that.
Okay.
And
Well,
so like okay, so before Pangea we had Rodinia, which forms like around like 1.1 or 1 billion years ago. But before Rodinia we have this Nuna or Columbia, which it seems to form like by probably around 1.5 to 1.6. The
okay.
formation time isn't really well constrained, I think, to be honest.
Yeah.
But the breakup time, or the maybe the better term is reorganization time, does seem to be pretty well constrained, partly by the belt. Um, and so, like we know, for instance, and so like the focus here is going to be on like on Western North America and how that fits in. And like so, the model there's sort of a lot of people, including myself, have favored is that we had like Australia next to sort of Canada and like the northernmost part of the U.S. And then we had East Antarctica connected to like the southwestern U.S.
Hmm.
And seemingly like they broke off at some point, maybe at roughly 1.3-ish,
Yeah.
because the paleomag indicates that Australia was like by about 1.2, where they have good, I think, paleomag poles, it was pretty far away.
Huh.
Um, but then, if you look at a lot of models for Rodinia, the next supercontinent, if you look at like the maps of Rodinia and Nuna, they often are quite similar.
Right.
North America is always in the center, and many of the same sort of surrounding continents are in similar positions, maybe not the exact same thing, which is one of the things I've always found interesting about this whole business. But it seems like we had this reshuffling that maybe it brought back Australia and Antarctica for Rodinia, but maybe in a somewhat different arrangement.
Hmm. And Tasmania's in there too somehow?
Yeah, so I think there's good evidence that Tasmania was kind of like a bridge between the Belt Basin and southern Australia.
Okay.
And that I mean there are rocks in Tasmania that may represent like the western edge of the Belt Basin. Um,
Okay, one more kind of preliminary, and then let's go to some slides. And this is a wild card. I don't know how you feel. This whole lower belt and upper belt is on top of the Lewis thrust. How how does that factor into the story? Is the entire belt somehow far traveled or exotic, or what's your just general view on that?
Yeah, I mean this isn't stuff I've worked on, but I
Right.
think it's well established that most of the belt as it's exposed at the Earth's surface that we can go and look at is a Lockthinus, meaning it's been transported in this case from west to east. There
Hmm.
are like some places where you can actually see its depositional contact with the underlying basement. So there's the Helena embayment, which is out in sort of west central Montana. There, it's sitting on basement, and then in the Priest River area, Priest River complex in northern Idaho, there's strongly metamorphosed sedimentary rocks that are most likely lower belts that appear to be on depositionally on older basement rocks and
Wow.
an older quartzite.
What's
Although
the
everything there is so like deformed that saying that's an actual depositional contact is not really clear.
what's the name of that gneiss in the Spokane area?
So there's the Hauser River gneiss, or wait, Hauser Lake gneiss
Hauser Lake.
is
Yeah.
that's supposed to be the Pritchard Formation, which is the lowest main unit of the belt.
Huh.
And then there's a quartzite called the Gold Cup quartzite, which is supposed to correspond to the Nyhart Formation, which is below the Pritchard, and people will variously say that it is or it isn't part of the belt. It may be significantly older or it may not be. But then there are like nice like orthogneisses below that
Huh.
that are 1.86 billion years old, and in other cases 2.6.
Okay, well, this is perfect timing for me and maybe many of the viewers because we've had general ideas about this old supercontinent and these nearby continents that are no longer around, but you've got some new data that's going to help us with some of these maps. So let's go ahead. If you can start with your slides, Rich, and occasionally I might interrupt, but for the most part, I think we've set the hook now. Let's just go ahead and get to some of your slides, and we'll just go for it.
Yeah, I should mention though that
Yeah.
that this the paper, the work, it's it heavily is the work of a master's student and an undergraduate student that worked with me.
Okay.
Um,
You want to name them?
so what?
You want to give their names?
Yeah, no. So there was Dina Amato was the master's student, and then Aaron Leonard was the undergrad.
Nice. And this paper, viewers, if you go to nickzentner.com and click on the word Alaska in the upper right, you'll get to this brand new paper by Rich, a new insight in Mesoproterozoic paleogeography from the age and geochemistry of detrital minerals in the Belt Supergroup. Okay, Rich, let's go. Let's look at these slides. I'm loving this topic.
So what is your interest here? What sparked your interest in the belt before I start?
I have been reading and trying to think about how I want to. I've announced that I want to do an Alaska series this winter, and to do that, I'm thinking my working model is that I'm going to start down here in the Pacific Northwest with some major narratives, and then try to follow them north. And I'm intrigued by the Rocky Mountain Trench and the Tintina, and then it's just kind of disappearing into this belt area. So that's ultimately why I'm kind of hesitating and looking a little bit more carefully at the belt and trying to learn some new things.
Okay. Yeah, so this is just a map of sort of Precambrian Laurentia, so ancestral North America here,
Hmm.
from one of the sort of classic belt papers, Ross and Villeneuve.
Yes.
You see the name. Um, And so this just shows you where the belt basin is. So it's this blob over here that is sort of right on the edge of ancestral North America. So
Hmm.
we have a rifted margin here that is more or less defined by the dashed line, I suppose. And so that rift margin formed in the Neoproterozoic from the breakup of Rodinia, not Nuna. Um, and there's really like very sparse geologic record between the end of the belt and and the Neoproterozoic, to be honest.
Yeah.
There are some like newly recognized sedimentary packages up in this area, including on top of the belt. But and there are these sort of cryptic metamorphic events that are recorded in the ages of garnets in metamorphosed belt rocks that are like Rodinia Formation age.
Hmm.
But it's all kind of mysterious what's going on between like 1.3-ish and like 1.3-ish and like really like 700 something MA.
Yeah, I think our viewers maybe are going to be shocked by the amount of unknowns, but come on, man, we're more than 1 billion years ago. What do you expect? Like
Yes.
this is not an Eocene story. I don't think so. Yeah, I mean it's totally reasonable to have tens and hundreds of millions of years go by and we got nothing to say, basically.
Yeah, so I mean, what you can see here is that we have a bunch of Archean cratons up in Canada that
Yeah.
are stitched together by in many cases, Paleoproterozoic orogenic belts.
Uh-huh.
And then we have a bunch of accreted terrains or seemingly accreted terrains in like southern Laurentia down here.
Yeah.
So Yavapai, Mazatal, and so forth.
Okay. All right. Well, we got the belt. Good. All right. Let's keep it going here. Oh, I love this map from the new paper.
Yeah, so this is my map. This is Jeff Land's map from
Okay.
his paper. I just reused it with their permission.
Got it.
So this just shows you the different units of the belt, also the basement exposures, which are the purple. The lowermost unit of the belt, well, what's okay? So like lower belt as a term is kind of just an informal designation that we use, and that's basically the Pritchard formation, which is enormously thick. It really should be a group, a Pritchard group, but
Hmm.
for whatever reason, it's still a formation because it's many kilometers thick.
Yeah.
And in some places, there are like a couple random units below the Pritchard, but up in sort of the area I was working in, it's just Pritchard, and that's the bottom.
Yeah.
And in most cases, again, you can't really see the actual bottom. It's just underground somewhere, or it's a thrust fault, that it's transported this big wad of material.
Right.
So the green is the Ravalli group. Oh, and the other thing about the Pritchard is that it's like, well, really all of the belt. It's pretty fine grained. It's like sandstones and siltstones, now quartzites in
Yeah.
some cases. There are some carbonates in the middle, but it's mostly relatively fine grained clastics. And so for the Pritchard, this is like turbidites deposited in relatively deep water.
Hmm.
So like turbidites are kind of like underwater landslide deposits from like slumping. So you have these like alternating, different beds. And the other thing about the Pritchard is that it is full of mafic sills that seem to have come in at the same time. So they were contemporaneous with the sedimentation.
Hmm.
And sort of this stuff altogether points to this being some sort of extensional basin, the Belt Basin. Um, I think one of the earlier ideas was that it was kind of like a Red Sea kind of environment.
Yeah.
But the implication there is that it's an opening ocean, and it doesn't appear to actually be an opening ocean. It appears to be like something
Wow.
closer to like a failed rift, maybe, or an intercontinental basin. The guys from this paper, I think they compare it to Lake Baikal or the Caspian Sea.
Okay.
And I guess that's another issue here is that there's been this long-running debate as to whether it's a sea with salt water or it's just a giant lake like in East Africa today.
Okay. Rich, can you stop your share? Like, I don't think we're into the main part of your paper, but like to me, I'm processing in real time. I mean,
Right.
I don't know if you can see this, Rich, but like I was just trying to just draw Glacier National Park with the lower belt. So both the lower belt and the upper belt, and this Pritchard stuff you're talking about is the lower belt, right? So
Yeah.
this is on top of this thrust fault. And now you're saying we got deep water, which not even shallow water. Is anybody saying that we're out in the water with the low belt, or is it just a,
Well, yeah, we're in water of some kind. It's just a question of whether it's a really deep lake or whether it's like an inland sea of some kind.
I see, but we're
Yeah.
still in the neighborhood of North America, I guess. We
Yeah,
have to
yeah.
be.
No, I mean, like an intercratonal basin might be the best way of thinking about
Okay.
it, but one that's, forming through extension of some kind because the mafic magmatism is sort of tied to, like at least attempted rifting.
Hmm.
But so what happens after the Pritchard, though, is that, and I should probably go to,
Oh, yeah, yeah, yeah.
uh, let's see.
Wow, man, I was so bored with the belt, but man, I'm not bored anymore.
Can you see this?
I can, yes, thank
Okay.
you.
Let's see. Wait. Where's my? Oh yeah, okay, here we go. Yeah. So this is a figure that like draws together the various age constraints for belt deposition.
Mm-hmm.
There's not a lot, but there are enough to sort of come up with this basic story, which is that the Pritchard, what you see here from Pritchard A to Pritchard H,
Yeah.
that's like, that's like over 5 kilometers or about 5 kilometers of sand and silt and mud. And it's deposited really rapidly. So what you see here is the age difference between the different units. So the fact that this line is like almost vertical means that the Pritchard is forming very quickly,
Wow.
a lot of material very quickly.
Wow.
Yeah.
And the dates are coming from the sills that are in this otherwise kind of homogeneous material.
Yeah, so that's a sill there, and the other dates are more from like ash layers,
Oh, wow,
which
really?
are like really hard to see and find in the belt. So
Yeah,
hats off to the people that do
right.
that stuff. Um, so
Okay.
after the Pritchard, we have the Ravalli group, which represents like a shallowing of the whole system. This
Mm-hmm.
is like probably like we're like this is some of this is like we have like wetting and drying features, I guess is what I'm trying to say,
Okay.
um, in the Ravalli. So these are like a lot of red beds and lots of mud cracks, stuff like that. The Pegan is a bunch of carbonates and then sort of more sandy materials to the west. And if you've ever seen the photos or seen them yourself in the field, the stromatolites in the belt, which it's kind of famous for, some of them are in the Pegan, especially in Glacier National Park, and there are other ones up in the Missoula group.
Yeah.
So with the Missoula group, we're back to clastic sands and silts and stuff.
Hmm.
And again, this seems to be like a series of alluvial fans in this shallowing, basin, whether it be a lake or a sea.
So, Rich, I think we're heading here, but I'm just going to jump in to remind our viewers, or I think I'm going to remind our viewers, we've got Tasmania and Australia here during most of the Pritchard. That's ultimately what you're saying with your new
Yeah,
paper.
that's what I would argue.
Yes. Okay. Well, and we're heading to that with some data, which I find fascinating. I'll bite my tongue till we get there.
Okay. Yeah, so I mean, this is sort of what you see in Glacier. So pretty much all the
Yeah.
rocks you see in Glacier, with very rare exceptions, are Belt Supergroup. It's just this immensely thick
Yeah.
wad of sediments. And I mean, here it's not even that thick relative to other places. Like
Huh.
it's insanely thick in like the Idaho Panhandle, although it's also dismembered. So I guess that's the other thing to think about with these thickness reconstructions is like, people have to like unmove all these thrust faults and then deal with normal faults that come in later. So it's just kind of a
Okay.
disaster unless you're a
Okay.
structural geologist and like that's your
Right.
thing that you like to do. So that's, and then, this is an example of the Missoula group. So you see these really nice ripple marks. So again, signs of very shallow water.
1.4 billion or whatever years ago.
Yes.
My God. Okay. Yeah, that I'll never get over that. Now, this is really what got me interested in geology, living in Glacier Park and seeing these things and hearing the dates. And I don't think I even heard about the match with Tasmania or Australia. I know I didn't 40 years ago, but man, there's a lot of really dramatic stories with this stuff. Please.
Yeah, I mean some of what's going on with this amazing preservation is that there weren't really things burrowing around in the mud to disrupt these features.
Yeah, yeah.
And also, I mean the rocks they've all been baked to some degree, so that they've
Hmm.
gotten a little bit harder than they otherwise would have been
Yeah,
when they shortly after they formed.
yeah. Good. Um, Great. Keep rolling, and I'm anxious to get to this data in the new paper eventually. Yes, thank
Yeah,
you.
okay. So this is just another strat column. This is from the Ross paper. So we might just skip this actually.
Yeah, yeah.
Yeah. So, we looked at we had a strong focus on the Pritchard and the Ravalli just because those are the ones that have previously been identified as having material from off North America, from some other continents. Um, so, and you can see that the Ravalli and the Pritchard formation, so these are zircon ages, Detrital zircon ages, and you can see that the Ravalli and the Pritchard, they're like remarkably similar to one another. I mean, it's almost an exact match. And in both cases, they have this really important peak around like between 1610 and 1620
Okay.
that doesn't really have a North American source, at least one that would be rich in zircons.
Here we go.
Um, so that is like the sort of key to all this stuff is that we have these non-North American detrital zircons. This is referred to sometimes as the North American magmatic gap. So this time between about like 1.61 or 2 and like 0.48, actually 1.48, that is. Um, and so if you compare this though to the upper belt units, the Missoula group and the stuff in the south that we call the Limhi, it's markedly different. The peaks here, the main peak is like 1.7, and that is like a very common igneous age in like southwestern US.
Okay, I'm going to stop you. Can you stop your share? I need to make sure I'm keeping up, but to me, this is the biggest message. I'm going to use my dorky little thing again. So we're talking about the lower belt, the Pritchard, the upper belt is the Missoula that you were just talking
Yeah.
about. And I think what you just said, Rich, is that essentially almost all, I'll just say sand, but I know it's a bunch of finer stuff as well. But the let's say sand and silts and muds in the lower belt didn't come from North America.
Well, I want to say that it all is from an exotic source, but much of it is. A
Much of
large
it
large
is.
portion of it is. There
It's
probably is some southwestern North American sand in there mixed in for fun, but I mean, you can see when you look at the peaks that the main peak by far is this, age interval that we don't really have
don't have.
much rocks to provide zircon around here in North America in general. At least like unless you go to like Labrador or someplace like that.
Okay. So to me, that is wild because I guess in the last 10 years, maybe I caught wind of this detrital zircon stuff, and I'm like, all right, well, Australia is offshore or connected to us, and so there's some rivers bringing a little sprinkling of Australia kind of mixing in with our stuff. But you're saying it's not even a mix in the lower belt, it's dominantly their stuff
It
that
would
is
seem
being
so, yeah.
deposited. I mean, I'm just stunned by that. You're not the first to say that, or are you the
No, not
first?
at all. No, I
Okay,
mean, that Ross paper was kind of the benchmark for this. They were
okay.
like the first people to do like a full detrital zircon survey.
God,
And that was like, what, 22 years ago. But I mean, they were like dealing with like, a couple dozen zircons per sample, just because of the methods they were using, which were
wow.
much slower.
Okay.
But I guess I
Yeah,
mean, the sort of main value add for this study is that we didn't just look at the zircon ages, but we looked at zircon chemistry and we tried to find other minerals that we could date, in addition to the zircon that could tell us about other aspects of the source areas, not just like when granites are forming, but like when the source areas were being metamorphosed, for instance.
good. Well, maybe in the last portion of what we do right here, I want to keep track of your valuable time. Maybe we have a map or two with your best. We're bringing that paleogeography into a little bit more specific focus. You said it verbally at the top, but can we see Australia and Tasmania where you want it placed based on that new chemistry as well as the detrital ages, please?
Yeah, so let's see here.
Dramatic reveal. Oh, yeah. Okay.
Yeah, so the big red thing, that's the Belt Basin. The little T guy is Tasmania.
Ha!
Um, so this is the Gawler craton here. Well, South stands for South Australian cratons, but
Thank you.
the sort of main element of that is the Gawler craton.
Okay.
And then this is the Terra Adeli East Antarctic craton. But what those things are like, those two things have been together, or they were together for like a very long time. They didn't actually break apart until like the Jurassic.
Hmm.
So like I guess that's the thing about Australia and Antarctica is that like they were pals for probably like a billion and a half years.
Uh-huh. Uh-huh.
Um, so their separation is a relatively new development.
But Tasmania is its own Tasmania is more like connected to us. Tasmania has not been a pal with Australia.
Well, I mean, it kind of has, but it would have occupied a sort of bridge position in this
Yeah.
model.
Yeah.
Um,
Yeah.
so this isn't really something that when Australia goes, Tasmania goes with it, I guess is how I would put it.
Okay.
But it's like the first thing that you would encounter if you tried to, well, I guess, swim in the giant lake from Montana to the
Yeah.
other continent.
And just I have fond memories up above Many Glacier Hotel in Glacier Park of this beautiful sill,
Yes.
this beautiful black stripe going across that everybody must notice, even people who don't know anything about geology, they must notice that black, I think it's called the Purcell sill. How does that fit into our story? What's the significance of the Purcell sill in Glacier Park?
Yeah, so I don't think that actually is the Purcell sill.
Oh,
The Purcell sill I think is much lower in the
oh,
stratigraphy.
really? Okay.
But the prominent sill that you see everywhere in the park is actually not related at all to this. Um, I think to the extent that it's been dated, it's thought to be like 700 something MA.
Wouldn't that be the breakup of
Well, the
Rodinia?
breakup of Virginia. So like
Okay.
long after Belt stuff is done. So
Yeah.
I mean, I would say that it's just completely unrelated at that point.
To
So I
the
guess the point there is that there are sills and stuff in the belt that are contemporaneous with belt sedimentation, but
okay.
then there are much, much younger sills also in the belts that are from like Rodinia breakup stuff in the 700s MA.
So somebody
If you've been to like Grand Teton National Park and you look up at Mount Moran, which is one of the more prominent mountains, it has this giant black stripe on it, and that is another one of these Neoproterozoic Rodinia breakup sills, or in that
okay.
case, a dike.
I'm sorry. Can you stop your share again? This is big. We're just tossing
Okay.
this in at the end, but like I hadn't had that before. So not all sills in the Precambrian have a specific story to tell. It sounds like the sills within the Pritchard, there's no breakup story there necessarily, or is
I
there?
would say it was like an attempted breakup or reorganization. And um, again, I mean, I said this in the very beginning. It's sort of like what happens in this long interval between the end of belt sedimentation and, the Rodinia breakup. It's kind of, there's very little rock record. We have a little bit, there have been these newly discovered sediments that are slightly younger than the belt. And I mean, they
Hmm.
probably have a key part of the story, but that's,
Hmm.
very new stuff.
Okay. Well, that whatever sills we can find in Grand Teton Park or Glacier Park that are in the 700 million year age ish, if those are signifying the breakup of Rodinia, I never had that before, and I love the elegance of that. And if most people are seeing that, in addition to the Grenville or what are the names of those basalts that are the Rodinia breakup as well that are like in northeastern Washington? I can't think of them right now, but
It's in northeastern Washington.
I thought there were some other.
Yeah, no, there are some volcanics, but yeah,
Yeah.
the name escapes me
Okay.
too.
Yeah.
But
I
there's
know.
up in like the Yukon, there's the Franklin large igneous province, which is also broadly Rhodinian breakup related.
Oh, really?
Yeah, and I mean that's also important because people link the eruption of that to snowball Earth events that happen late in that whole breakup process.
Well, things are getting wild here at the end. I
Yeah.
love it. I love
Yeah.
it. Are
But
there
the
any?
Rodinia breakup dikes and sills in like Montana and Wyoming and so forth that's like broadly referred to as the gun barrel dike swarm.
Okay. Huh. Uh, we can kill it here, or is there anything? Was there another map or something you wanted to share with us? Are we doing your new paper a service? I mean, it feels
Well,
like
yeah, I would just want to show a couple other things.
good. Yeah, let's do that.
Let's see here.
Wow. I
Yeah, so
love I,
like,
I love these little tangents. It must be frustrating when somebody comes on here, but at the same time, I love these little casual bombs that are dropped, and then I'm like, wow, holy cow, I got to go follow through on that. Okay, yeah, let's do a little bit more from your paper. Thank you, Rich.
yeah, so what we were really trying to do with this study was to try to isolate other uranium bearing minerals that we could date that would tell
Hmm.
us that would provide like additional dimensions of information about the belt sand source areas. And
Okay.
so there's this mineral called monazite, which is it's a rare earth element phosphate. So it's like, it literally has like cerium in its formula. So a pretty
Hmm.
strange mineral, to be honest.
Hmm.
Um, but that's a mineral that mostly forms during like relatively high grade metamorphism. So it's a metamorphic mineral that you can date the timing of metamorphism.
Okay.
And it doesn't survive nearly as well as zircon does in sedimentary systems, but sometimes it does. So
Hmm.
We had monazite in, a couple samples that we were able to isolate and date. So we were able to directly compare the zircons and the monazite ages for the same sample. And in some cases, there are pretty dramatic differences in sort of what they tell you. So, I mean, I would probably the most dramatic was in the Missoula group, where we see these southwestern U.S. metamorphic events that are like post-dating the big granite formation events.
Yeah.
So what you see basically here, the difference between the blue and the red, and the blue and the red here. So they're, significantly offset. And then the third mineral is rutile, which is just titanium oxide, and that is again a mineral that is mostly forming in metamorphic environments. But in that case, the uranium clock that it contains doesn't actually start keeping time until it cools below about 500 degrees Celsius.
Hmm.
So this is more of a thermochronometer. So it's telling you, or at least it can be telling you, when the source regions were exhumed close or closer to the Earth's surface.
Okay.
So typically, like when people look at these minerals together, it's fairly common to have the rutile be significantly younger than like the zircon or the monazite, and we do see this. You can
Huh.
see that's the grain here.
Yeah, yeah, yeah. Okay. Good.
So, and I guess the other thing, yeah. So this was just, I think, a cool thing that I put together. Just because of when the paper was written, there were a bunch of studies on Tasmania and geology just coming out like as I was finishing this paper, and the similarities between not just some of the sedimentary rocks there, but some of the metamorphic rocks there with the belt story are kind of amazing.
Hmm.
So there's this sedimentary sequence called the Rocky Cape group in Tasmania that has previously been tied to the Missoula group of the belt, which is what sort of is going on here.
Mm-hmm.
And then the upper part of the Rocky Cape group, it may actually correlate with this slightly younger Detrital group, which is in northeastern Washington.
Okay.
Um, but there are also these metamorphic rocks adjacent to the Rocky Cape group in Tasmania that are like schists and quartzites. And lo and behold, one of these schists is full of mafic sills, or in this
Ha!
case, boudins that are the same age as the sills in the Precambrian.
Oh, wow. How did you, so did you just read papers or did you start collaborating with the guy named Jack Mulder? Have you been working with him?
Well, I like was sort of hinting upon this in the first draft of the paper, and he was one of the reviewers, and he like suggested that I like flesh this out more,
Nice.
you know.
Okay.
But yeah, so he did a lot of the work on the Rocky Cape group.
Very fun. Well, yeah, I love this slide. That's in the new paper and spent a lot of time thinking about that. You want to stop your share and we'll say goodbye and maybe do some closing thoughts. Are you
Sure.
going to continue with this or are you on to other things, Rich?
I mean, the belt stuff, I have another paper to write from that data, which is on the sort of metamorphic story within the belt. So, what
Okay.
happened to it f over the last 1.4 billion years as it
Ha,
was sitting in the ground?
ah,
Um,
okay.
but yeah, I mean, I'm working on mostly other stuff now. So this
Wonderful.
was like this was all funded by the National Science Foundation, and that grant has been done for a bit of
Okay.
time.
Very good. Well, please hold the line, Rich. I'm going to stop the recording. We can chat for another minute or two.
Sure.
But Rich Gaschnig, University of Massachusetts Lowell, thank you for your time this morning.